Hello and welcome to our presentation on exponential families. Today, we're going to look at the Gaussian distribution with an observed mean. First, you need to know what an exponential family is. An exponential family is a set of probability distributions of a certain form. The Gaussian distribution belongs to the exponential family of this form. The form is shown below, where eta is the vector of the natural parameters. We will now briefly discuss the mathematical components of the equation. As you can see, the equation here calculates the probability of a random variable x taking on a certain value given theta. This is calculated by taking h of x, which is the base or the underlying measure, and multiplying this with g of eta, which is referred to as the partition function. This is then multiplied with the exponent of eta, which is the natural parameter, multiplied with u of x, which is also referred to as the sufficient statistic. Alright, it's time to meet the family. As shown in the previous slide, the equation here displays the form a member of the exponential family can take on. The normal distribution, the exponential distribution, the beta distribution, the gamma distribution, the Poisson distribution, the binomial distribution, the multinomial distribution, the chi-squared distribution, the Bernoulli distribution, and many more are members of the exponential family. To show you how a given distribution can be rewritten to prove that it's part of the exponential family, we take the Gaussian distribution as an example. Here you see the equation of the Gaussian distribution. This is what the graph looks like. The Gaussian distribution calculates the probability of the random variable x taking on a certain value, for example 10, given mu and sigma squared. This is what it looks like. Here on the left-hand side, you see the Gaussian distribution in the form of a graph. So on the x-axis we have x, the random variable. Mu is the expected value, aka the mean, and sigma is the standard deviation. The sigma squared depicted in this equation is the variance, which is just the standard deviation squared. The standard deviation sigma to the right of mu plus the standard deviation, which is sigma to the left of mu, is 2 sigma. This is because 1 plus 1 is indeed 2, or so I've been told. The y-axis depicts the probability that the given x value has. So if the x value takes on the value of mu, the probability is the highest, right here. Now we'll do the math. Right here you can see the Gaussian distribution, and we want to rewrite it so it takes on the form of the exponential family, with these components highlighted here, 1, 2, 3, 4. In our example, mu is known, so we could treat it as a constant. We could assume an arbitrary value of mu, but here we just set it to 0. If mu equals 0, here we can just let mu drop out. So when you compare these two equations, mu is just gone, both here and here. As you know, the root of sigma squared is just sigma, so now we can take sigma out with 1 over sigma. Now we can factor out x squared right here. As you can see, our equation is taking on the form of the exponential family. The colors show you what is what. So now you can see the current form of the Gaussian distribution and the form of the exponential family side by side. And you can see that h of x corresponds to this, g of eta corresponds to this, eta is this, and u of x corresponds to x squared. But you may have realized that g of eta does not have eta anywhere represented in the function. So we want g of eta to depend on eta. Right now it only depends on sigma. So therefore we want to replace sigma with eta. This is what we're going to do now. So here you have eta, and that equals negative 1 over 2 sigma squared. We got this from here. So now we multiply with sigma squared, and that obviously gets us to eta times sigma squared equals negative 1 over 2. Now we want sigma squared by its own, so we divide by eta. This is what we get. Now we want to take the root, because we only want sigma. So here we take the root, and we rewrite the root of negative 1 over 2 eta by writing the root of negative 2 eta to the power of negative 1. Now we have sigma. So since we now have sigma, we can plug sigma into this function here. So 1 over this. And now our g of eta depends on eta. This is what the whole equation looks like now. So now we have proven that the Gaussian distribution takes on the form of the exponential family, and therefore it is part of the exponential family. These are the components. That's it. Thank you for your attention.